Okay, let's talk about written assignment 7. Um, this seemed to be helpful for at least a few students last time I did it for the previous assignment, so I guess we'll keep doing it. I don't mind. Okay, so for this one, we only had one problem. Remember, you're welcome. Let f of x equal e to the x over x, and we want to graph, or I should say, sketch a graph of f of x. Right. Okay. All right. So remember that there are 4 steps, which the inferior Nick showed us. So he calls it step 1. I'll use A because I've already started numbering here. Is we want to find asymptotes. Okay. And then B, we want to find critical points and inflection points. Part C, want to find intervals of increasing, decreasing. And then finally, we want to find out where this thing is concave up versus where it is concave down. And then we'll be able to actually graph the thing. Okay, so let's start with part A, asymptotes. Okay, so let's remind ourselves of the function up here, just so we sort of have it floating around. Let's talk about vertical asymptotes first. Okay, so it seems that x equals 0 is a candidate, right? This is a place where the function is undefined, but we have to verify that it is an asymptote, right? Many of you lost points on this on the exam. Simply finding out where the denominator is equal to 0 isn't quite good enough, because there are definitely examples where a problem with the domain in the denominator leads to, say, a hole in the graph as opposed to a vertical asymptote. So how to verify is we need to take the limit as x approaches 0 from the right of the function. And we also need to take the limit as x approaches 0 from the left of the function. Okay, so remember that how this typically works is we usually get something which looks like a number over 0. In this case, I get e to the 0, which is 1, over 0. All right, so this is a good sign. This is usually what vertical asymptotes look like. This almost gives it away, but we should probably double check just to be sure. So how we do this is we check a value which is very close to 0 on the right side, meaning approaching it from the positive side. So let's say 0.1. So we have e to the 0.1 over 0.1. And now I don't care what the value of this thing is. All I care about is what's the sign. And the sign is positive over positive, right? E to the anything is positive, 0.1 is certainly positive. So this is, I should say, greater than 0. Okay, so this limit here is really, I don't like how I've written this here. I'm going to move this. I'll put this over here. And I'll say that this is positive infinity. You don't need the plus. I'm just doing this to emphasize, right? So it's of this form. So I try a point which is close to the value that I'm approaching. See what sign I get. That sign determines what sort of infinity this approaches, right? Remember, if I get this, as a one-sided limit, it's going to be infinity of some kind. This just determines whether it's positive or negative. Same thing over here. I get 1 over 0. Okay, it's going to be infinity of some kind. I just don't know if it's going to be plus or minus here. So let's try x equals negative 0.1. So I get e to the negative 0.1 over negative 0.1. All right, so e to the anything, like I've said, like I said for this last example, is positive, right? Doesn't matter what the exponent is, e to that number will always be positive. In fact, any number raised to, any positive number raised to an exponent will be positive. As for the bottom, that's clearly negative. So I have a plus over minus means I get minus infinity. Great. Now, not only does this guarantee that we have a vertical asymptote, but it gives us the shape that we need, right? This is going to be helpful when we actually graph. So we do have a vertical asymptote of x equals 0. Okay. How about horizontal asymptotes? Well, for this, we need to check the limit as x goes to infinity of the function and the limit as x goes to negative infinity. Negative infinity of the function. Okay, so this is infinity over infinity, pretty clearly, if I just plug in. So I can use L'Hopital's rule here, because it's the proper indeterminate form. The derivative of the top is e to the x, derivative of the bottom is just 1, and this is clearly infinity, right? Infinity over 1. Great. Now, as for x approaches negative infinity, it's going to be a little different, right? Because as x approaches negative infinity, remember what the graph of e to the x looks like. I have something that looks like this, right? Where I have a horizontal asymptote at 0, and that happens as x approaches negative infinity, right? So as x approaches negative infinity, this thing approaches 0, so I have 0 over something going to negative infinity. Okay, well I'll put this in quotes because it's a little hand wavy here, but 0 over something getting bigger and bigger and bigger, or more negative, more negative, more negative, is simply 0. 0 divided by any number still gives me 0, as long as the bottom is not 0 itself. Okay, so I do have a horizontal asymptote of y equals 0. So I will unbox that and I'll say, therefore, horizontal asymptote of y equals 0. This is what I have. And I have a vertical asymptote of x equals 0. These are two things we'll have to remember. Okay, now finally for slant asymptotes, remember the only time I have a slant asymptote is when I have a polynomial over a polynomial such that the degree of the top is 1 greater, exactly 1 greater than the degree of the bottom. For example, x squared plus x plus 1 over x minus 1. In this case, I will have a slant asymptote. However, non-example, this is something which doesn't have one for a multitude of reasons, right? This clearly doesn't have a degree greater than, well, 1 greater than this because, well, it's not even a polynomial, right? It's an exponential function, right? So there's no way to divide x into e to the x to give you a linear function. So there is no slant asymptote. Okay, great. That takes care of part A. Now let's move on to B, which is critical points and inflection points. Okay, so remember we have f of x equals e to the x over x. And to find critical points, we take a derivative. This is going to be a quotient rule. So I have bottom times the derivative of the top minus top times derivative of the bottom, which is just 1. All over bottom squared. Low d high minus high d low. Square the bottom and away we go. So we have this and we want to set it equal to 0, and you'll see me sometimes write or infinity. And this just means look for problems with denominator. This just means look for where the denominator is equal to 0. Now, notice that we've already shown x equals 0 is a vertical asymptote. So we can ignore the denominator here. Here. Okay. What this means is x equals 0, as soon as it's a vertical asymptote, has to be built into our number line when we're looking for increasing, decreasing already. So there's no reason to look at this x squared being 0 because it's the same thing as x equals 0. Moreover, if there's an asymptote at x equals 0, then of course there's not a critical point, right? This doesn't mean that it can't change sign at x equals 0. The function can still have the form going up, vertical asymptote, and then coming down, right? Over here I'm increasing, and over here I'm decreasing. These changes don't have to take place at a critical point. They could take place at a critical point or an asymptote. But all we're trying to do here is find critical points. And a vertical asymptote is absolutely not a critical point because it's not a point, right? So we can simply ignore vertical asymptotes when we do this computation. So we need to have x e to the x minus e to the x equal to 0. So how do I solve this? I can factor out an e to the x. Oh, what am I doing here? I can factor out an e to the x, and then I have x minus 1 equal to 0. Great. Okay, now what? Well, that means either e to the x equals 0 or x minus 1 equals 0, or both, right? But of course, this is impossible. E to the x is never equal to 0. It's always greater than 0. So I only have a critical point at x equals 1. So my critical point is there's only 1. 1 is the input, and the output is f of 1. Right? I plug into the original function to get the y coordinate. 1 comma e, right? E to the 1 over 1. Simply just e. Great. And here's my critical point. Okay. Now let's look at the second derivative. Remember that our function is e to the x over x. Our first derivative was x e to the x minus e to the x over x squared. So our second derivative is just another application of the chain rule. or of the quotient rule. But of course, there's going to be a product rule involved there too. So this is a little bit more complicated, but not terrible. I have the bottom times the derivative of the top. Now the derivative of the top is a product rule here in this term. So I have the first times the derivative of the second plus the derivative of the first, which is just 1, times the second, e to the x. Oh, sorry, not done yet. I have to remember this minus e to the x. I have to take the derivative of this, but this is just the same. So this is minus e to the x. Okay, that takes care of the bottom times the derivative of the top minus the top times the derivative of the bottom. And this is easy. It's just 2x. All over the bottom squared, right? X squared squared gives me x to the 4th. And let's do some simplification here because it looks like there's going to be some stuff that cancels. Quite obviously, this e to the x and this e to the x go away, right? We don't need to distribute the x squared to see that, right? These are certainly going to disappear. So I get out of this first term just an x cubed e to the x minus, now I'm going to distribute through. 2x times x e to the x gives me a 2x squared e to the x. 2x with this minus here times negative e to the x is a plus 2x e to the x. All over x to the 4th. All right, and one more simplification I can do is that I can cancel one of these x's, right? Because there's an x in each term. So I can factor it out of everything and then cancel it with one of these. I won't do it in multiple steps. I'll just do it in one. So this is x squared e to the x minus 2x e to the x plus 2x, 2 plus 2 e to the x over x to the 3rd. Right. Canceled 1, 1, and 1. Great. Okay, and now I want to find out where are my inflection points. Well, they can only occur when the second derivative is equal to 0. Now, finding solutions to this will not guarantee that I have inflection points, right? These are just the possible candidates. But we'll find, again, we can ignore because we've already taken care of x equals 0, right? This already is going to appear on all of our number lines that we need. So there's no reason to include it. So I have x squared e to the x minus 2x e to the x plus 2 e to the x equals 0. All right, so I can factor out an e to the x. And I'm left with x squared minus 2x plus 2 equals 0. E to the x is never 0. So I don't have to worry about that. I just have to worry about x squared minus 2x plus 2 being equal to 0. To figure this out, this isn't something you can factor, but we know how to deal with this. We're grown-ups. So this is just an application of the quadratic formula. I have negative b, which is 2 plus or minus. This is screwing up on me. Plus or minus the square root of b squared, 4, minus 4ac. This is 4 times 1 times 2 over 2. Notice this gives me a negative 4, so I get an imaginary root. So this, not real. And of course, in this class, we're only dealing with real numbers. So we don't count this, no inflection points. Great. Now this, again, does not mean that there's nowhere where I change concavity. Again, I can change concavity at a vertical asymptote, and we'll see that in a few minutes. But first, we're going to move on to the increasing and decreasing part. So C, we want to find out where is this thing increasing and where is it decreasing? Okay. So remember, for this, I want a number line, and I want to plot any vertical asymptotes, 0, and I'm going to have to remind myself what my critical points were. 1 comma e was my other one. So the x value is the only thing we're using here, so I need 1. Okay, so I have my number line. A little lopsided, but that's fine. All right, so now I want, and I'm going to remind myself of the original function, and then its derivative, x e to the x minus e to the x over x squared. I'm going to need this just to work with this thing. All right, so I have this table that I've been using, intervals, test point, evaluation, and finally the sign. Okay, so I have my interval of -infinity to 0, my interval from 0 to 1, and my interval from 1 to infinity. That's sort of how this is partitioned. And I need some test points. So the obvious one here seems to be x equals -1, but any point in this interval would work. Just seems like this is the closest whole number to the endpoint, or the smallest possible endpoint, or the smallest possible whole number. And I want to plug this into the first derivative. So I plug it in, and I get -1 e to the -1 minus e to the -1 over 1, right? -1 squared, I guess. Okay, so I have a negative e to the -1 minus e to the -1. So this is -2 e to the -1. E to the -1 is positive. So this is going to be negative on the top. I have a -2 times a positive number, and then a positive on the top. So this is negative. Okay, I'm going to make a little bit more room here. 0 to 1, and then down here we'll do 1 to infinity. Okay. And I apologize for any background noise. I'm currently at my parents' house. They're watching TV and other things. So let's take x equals 1/2 here, because it just seems like, well, there's no whole numbers in there. Let's just take the nicest fraction we can have, and 1/2 seems to be that. So I have 1/2 e to the 1/2 minus e to the 1/2 over 1/2 squared. All right, now let's think about this. I have 1/2 of something minus 1 of that thing. In fact, it might even be easier to write this as e to the x times x minus 1 over x squared. And now, this might be a little bit more obvious. Now I have e to the 1/2 times 1/2 minus 1 over 1/4. We're all adults here. We know that 1/2 squared is 1/4. So I have a positive number, e to the 1/2. E to anything is positive. And then I have a negative number, 1/2 minus 1. And then I have a positive number on bottom. So I get a negative, I don't know why I drew that there, a negative over a positive. So this is also negative. Okay? And let's take x equals 2 and do the same thing. E squared, 2 minus 1 over 4. Positive, positive, positive. Positive over positive is greater than 0. Great. So this tells me I have a minus here, a minus here, and a plus here. Great. All right, the graph is starting to shape up. Okay, so now let's move on to part D. This is finding intervals of concavity, concave up, concave down. Right. Okay. So again, just as before, we have a number line, and we have to figure out what goes on this number line. Well, we've sort of already done this work, and I'll write the function in second derivative here. Let's see if I can remember it. Squared e to the x minus 2x e to the x plus 2 e to the x all over x cubed. I believe this was the simplified form. And even more so, it'll help us computationally, just like last time, just like in the increasing decreasing case, to write it as such. Okay. All right, so remember that we found that there are no inflection points, right? So the only thing I have to do is include the vertical asymptote. Now, note, vertical asymptote needs to appear in every number line. What this means is, as soon as you find that the function has a vertical asymptote, and this is why you do it first, that value, the location of the asymptote, needs to be on the number line for increasing and decreasing, and the number line for concave up and concave down. Once you found it, it has a ticket to be on every number line that appears for the rest of the problem. Because I can always have a change in concavity or a change in increasing and decreasing across a vertical asymptote. This is always possible. So even if the problem tells me I have no inflection points, I still may have a place where the inflection changes. It's just not necessarily a point. It could be an asymptote. Okay, so let's build a table similar to what we did last time. We have intervals, test points, evaluation, which I'll give a little bit more room this time because it's a little bit more complicated. And then finally the sign, which is the thing that we're really after. Do that, that, that. Okay. The only two intervals I have are negative infinity to 0 and 0 to infinity. Easy test points here. X equals -1 and x equals 1, right? And we just plug in, right? So I have e to the -1 times 1 plus 2 plus 2 all over -1, right? Because I have a negative raised to an odd power. This is -5 over e, which the value is not important, the sign is. So over here I write concave down. And this is just the symbol I use for concave down. I don't like using pluses and minuses on here, just because when I'm looking back on my work, it's confusing to me which one of the number lines is the increasing, decreasing one, and which is the concave up, concave down. This makes it a little bit more obvious. Okay, so now I have, for the test point, x equals 1 in the interval 0 to infinity. I get e to the first, which is just e, times 1 minus 2 plus 2 plus over 1. And this is just e, right? Because I have -2 and +2 cancel. E times 1 gives me e. And this is, of course, positive. Concave up here. Now, this table is certainly not necessary, even for the increasing, decreasing part. It's just a good organizational tool, and it helps me personally when I'm doing these. This is the necessary part. So if you'd like to skip the table and it's just clear to you what goes where and why these are what they are, still show a little bit of work. I mean, still sort of pick a test point. It doesn't have to be organized in this way. But this is sort of the critical part of it. All right, so those are my intervals. And we can finally let's learn how to write English. Finally, we can graph. Great, and we'll act like we're excited about it. So I'll have my axes here, And let's go back and read through this in order. Now, it's good that this has taken up a couple of pages because this is something which is going to happen. These are long problems and they get complicated, and it's very easy to make mistakes if you're not organized. So you'll notice that I've made the point of boxing or sort of isolating the important things, right? This is a big jumble of work, and if I'm looking at this in a notebook without these, individual slides, it's going to be even more difficult to find out what's important, unless I emphasize the important things, right? So here I have a vertical asymptote of x equals 0, okay? And I have a horizontal asymptote of y equals 0. And remember that this y equals 0 comes from the left end behavior, right? Not the right. As I approach the right, as I approach positive infinity, this graph goes to infinity. But as I approach the left, meaning negative infinity, I get y equals 0. So this is just to get our asymptotes written in there and to expect what should come out of the graph when we're done. And I'll try to sort of separate it out so you can see that I'm actually drawing it. And of course, these should be right on the axis, but you wouldn't be able to see it otherwise. Okay, so I have my asymptotes. Dotted lines are fine. You don't really need to label those. And now let's go back and find out what we need to do next. Well, we don't have any slant asymptotes. Great. I've made that very clear right here. No slant asymptote, so I can just ignore this part. Critical point. Okay, have my critical point here. 1 comma e. All right, let's plot that. And when you're graphing these, just eyeball it, right? E is somewhere between 2 and 3, so yeah, that looks good. And the option is yours. You can either label the axis appropriately, like this, with 1 and e. This is clearly the point 1 comma e. Or if you want to just, sort of put it in space, that's fine. Just make sure you're labeling with this. So one or the other, if you do both, that's fine as well. But I'm going to stick with just labeling the axis because the picture gets a little crowded if you put the ordered pairs in there. Okay, so I have one of my important points. Now let's look for inflection points. Thank you, past Nick. I reminded myself that I don't have any inflection points. Great. Now let's look at intervals of increasing and decreasing. And I like to look at these in conjunction. Oh, I'm sorry about that. Whoa, almost died. Okay. I like to look at these in conjunction with intervals of concavity. So from negative infinity to 0, I'm going to be decreasing the whole time. What am I going to be doing in terms of concavity? I'm going to be concave down. Okay, so decreasing and concave down. I know what that looks like. And I also remember that my left end behavior is approaching 0. So either way, I'm going to have something sort of coming out flat along y equals 0 here, right? And if I'm going to be decreasing and concave down and approaching this vertical asymptote, and if you remember, as I approach 0 from the left, I'm approaching negative infinity. It has to be that this is my shape. And I guess that should probably hug the, I'll try that again. Something like this. More or less, right? Because my left end behavior approaches y equals 0. As I approach 0 from the left, I dive down to negative infinity. This is decreasing, and it's concave down. Great. That takes care of this whole half of the graph. All right. Now we have the question of what happens between 0 and 1. Okay. It's going to be decreasing and concave up because it's concave up all the way from 0 to infinity. All right. So it's going to be decreasing, concave up. And remember that our end behavior, or not our end behavior. As we approach 0 from the right, limit as x approaches 0 from the right of e to the x over x equals infinity. This is a little bit easier to remember if, all the work is right there in front of you. I have to keep flipping back and forth. But I have this limit approaches infinity, positive infinity. So it's going to look something like this. And remember, I have a slope of 0 at this point. So either this is going to flatten out and continue down, or it's going to turn around and come back up. And we'll have to figure out what's going on after that. But it's decreasing, it's concave up, and I have my infinity behavior up here. Okay, now from 1 to infinity, I'm increasing and still concave up. So this means I act something like this. And this again makes sense with our end behavior. Remember that the limit as x approaches infinity, positive infinity, is infinity. So this thing goes up and up and up forever and ever. So this is the sketch of our graph f of x equals e to the x over x.